sun revolves around the earth like that. You can see this scenario is going to be the equinox. You can see it's the equinox because the sun is perpendicular to the equator. So the sun is right over the equator. Okay, so now I'll rotate the sun around to the solstice point. That's the summer solstice because the sun is parallel to Earth's tilt. That's the summer solstice, the longest day in the northern hemisphere. So we have a 90-degree difference in location of the sun versus the Earth. Now, let's reverse the two. Okay, now that we've rearranged our configuration with the sun in the center, with Earth orbiting, let's see what happens. Now, is the Earth's tilt now parallel to the sun? No. Equinox. Still equinox. The tilt angle of Earth, when it orbits the sun, has no ability to change its orientation because, as we saw earlier, it would need to be aligned with the tilt, parallel to the tilt. But as we can see, it doesn't do that. Now, Copernicus was aware of this, and this is the reason why he introduced the third motion of the Earth.
Therefore follows the third motion of declination, also by an annual revolution, but in the opposite direction, that is, reflected against the motion of the center.
Since he knew if the Earth had no third motion, it would stay always the same season. You would always see the sun rise in exactly the same location throughout the year.
No inequality of days and nights would appear, but always either the solstice or the winter or the equinox or the summer, or in any case, the same quality of time would remain similar.
But stationary in the center, as the sun swings around, the relationship between the tilt and the sun automatically adjusts with simply the sun orbiting. Now, you either need a third motion for Earth or the heliocentric model doesn't work. Copernicus was aware of it. He provided it. Of course, in the heliocentric model, there's only two motions: the spin daily and the orbit, the orbital motion. The third motion is the great year, and that's a multi-thousand year cycle.